In this video, we're going to learn how to solve a differential equation using a power series centered at x is equal to 0. This is a classic example used to introduce power series, and the solution that we end up with you may already be familiar with if you've solved this second order constant coefficient equation before using the characteristic equation method. Learning how to solve a differential equation with power series is really important because some more complicated differential equations can't be solved with an easier method. To make things easier, I've written down some steps that we can follow, and these will work for solving any type of differential equation using a power series. We'll walk through these steps one by one as we work through our example. The first step is to write down the equation and the power series representation for y. The differential equation that we're going to be solving is y double prime plus y is equal to 0. And we're going to assume that the solution y has the form of this power series. The sum from n is equal to 0 to infinity, c sub n times x to the n. You also may see this written as a sub n instead of c sub n. The second step is to differentiate y and substitute the derivatives in y into the equation. In our equation, we need to find y double prime, so we'll start by finding y prime. Y prime is going to be the sum, n is equal to 0 to infinity, and now we're going to differentiate x to the n. So we get n times c sub n times x to the n minus 1. Now we can find y double prime. This is the sum. N goes from 0 to infinity. We differentiate x again, and this gives us n times n minus 1 times c sub n x to the n minus 2. Now what we're going to do is we're going to substitute y double prime and y into this equation. Our equation is y double prime plus y is equal to 0. So we have the sum, n goes from 0 to infinity, n times n minus 1, cn x to the n minus 2, plus y, which is the sum, n goes from 0 to infinity, cn times x to the n, and that's equal to 0. In a minute, we're going to combine these two sums, but for now, we're going to leave them as two separate sums. Let's copy this over to the next page, and we can talk about step 3. In step 3, we are going to eliminate any 0 terms, reindex the series, and then write the equation as one power series. This first power series is going to have two 0 terms. If we look at this expression right here, we can see that this is going to be equal to 0 when n is equal to 0 and n is equal to 1. What we're going to do is not include the summation for n is 0 and n is 1, and our sum is going to start with n is equal to 2. So we have the sum, n goes from 2 to infinity, n times n minus 1, cn x to the n minus 2, and then for our second sum, it doesn't have any 0 terms, so we're just going to rewrite it. That's the sum, n goes from 0 to infinity, cn x to the n, and that's equal to 0. Now we're going to do what's called reindexing the series. To reindex each series, we're going to let the power that each x is raised to equal to another variable, and I'm going to choose that variable to be k. In our first sum, we're going to let n minus 2 equal k, and then in our second sum, we're going to let n be equal to k. Let's go back to the first sum, and let's look at our index right here. We need to know what this index is going to be in terms of k, so when n is equal to 2, we have to figure out what k is. When n is 2, k is going to be 0. And then to rewrite this in terms of k, we need to know what n is. So we're going to solve for n, and we get that n is equal to k plus 2. Now let's look over here on the right. This one's pretty straightforward, but let's just write down when n is equal to 0, k is also equal to 0. Our first series is the sum. N goes from 2 to infinity, so this is now k goes from 0 to infinity. We have n, which is now k plus 2. And then we have n minus 1, which is k plus 1. C sub n is now c sub k plus 2. And that gets multiplied by x to the n minus 2, which is x to the k. Now for our second sum, this is the easy one. N is now k, so we have k goes from 0 to infinity, ck times x to the k, and that's equal to 0. Now we're all set to go ahead and combine these two summations into one summation. We have the sum, k goes from 0 to infinity. Our coefficients are k plus 2 times k plus 1, c sub k plus 2, plus our coefficient from our right summation, which is just c sub k. This multiplies x to the k, and we set that equal to 0. Let's now move on to step 4. In step 4, we are going to set the coefficients, that's all of this right here, equal to 0, and we're going to find what's called a recurrence relation. A recurrence relation tells how each coefficient is related to an earlier one. We'll take our coefficients, which are k plus 2 times k plus 1, c sub k plus 2, plus c sub k, and we're going to set that equal to 0. You always want to solve for the coefficient with the higher index. That's this coefficient right here. So we have c sub k plus 2 is equal to minus c sub k, all divided by k plus 2 times k plus 1. And this recurrence relation is going to be valid starting with k is equal to 0. Let's look back up and I'll show you where this comes from. It comes from right there. So we just need to mark down that k is greater than or equal to 0. I'm going to go ahead and highlight this because we're going to need this for our next step. In step 5, we're going to find an expression for each coefficient until we see a pattern emerge. I think this is the hardest step out of all of them. We're going to start with k is equal to 0, and we're going to substitute this value of k into our recurrence relation. When k is 0, k plus 2 is 2, so we get c2 is equal to minus c0, all divided by 2 times 1. When k is equal to 1, k plus 2 is 3, so we have c3 is equal to minus c1, all divided by k plus 2, which is 3, and then k plus 1 is 2. Now let's do k is equal to 2, and we get c4 is equal to minus c2, all divided by 4 times 3. Now we have to do something a little bit different than what we did for c2 and c3. Notice that c4 contains c2, and we already found what c2 is. So we need to rewrite this and substitute in what c2 is. The two negatives are going to cancel, and we're going to get c0, and in the denominator, we're going to have 4 times 3 times 2 times 1. Let's now do k is equal to 3. So we have c5 is equal to minus c3, all divided by 5 times 4. Now we're going to substitute in for c3. The two negatives are going to cancel, and we get c1, all divided by 5 times 4 times 3 times 2. Let's now do k is equal to 4. So we have C6 is equal to minus C4, all divided by 6 times 5. I feel like we're beginning to see a pattern emerge. Now we're going to substitute in for C4, which is this part over here. We don't have negatives that are going to cancel, so this one does have a negative, so this is minus C0, all divided by 6 times 5 times 4 times 3 times 2 times 1. Let's go ahead and just do one more, and I think this will be then enough to really see our pattern. When k is 5, we get C7 is equal to minus C5, all divided by 7 times 6. We're going to substitute in for C5. That's this part over here. And we have a negative, but now it's minus C1. And we have 7 times 6 times 5 times 4 times 3 times 2. And we can always put a 1 there too. Now I think we have enough to be able to see a pattern. One thing that I think we need to do first is we need to rewrite all of our constants in terms of factorials. Let's go back up to k is equal to 0, and we're going to write this one as minus C0 over 2 factorial. C3 is going to be minus C1 over 3 factorial. C4 is C0 over 4 factorial. C5 is C1 over 5 factorial. Now we're going to pick up a sign change. C6 is minus C0 over 6 factorial. And then C7 is minus C1 over 7 factorial. Let's now think about the pattern. Notice that when k is even, the constant is written in terms of C0, and the sign alternates. And then when k is odd, the coefficients depend on C1, and those signs also alternate. Let's now look at step 6. Step 6 is our last step, and in this step, we're going to write down the power series solution. We're going to start by going back to what we had written down for y originally, and that was y is equal to the sum. N goes from 0 to infinity, Cn x to the n. Let's write out what these terms are, and then we can relate them back to what we just calculated for the coefficients. This is C0 plus C1x plus C2x squared plus C3x cubed, and then all the other terms. Now what we're going to do is substitute in for the coefficients. We had our even coefficients, and then we had our odd coefficients. This gives us y is C0, which is just C0, and then we have plus C1x, and now we're going to substitute in what C2 is. C2 from the previous page was minus C0 over 2 factorial, and that multiplies x squared. And then we have C3, which is minus C1 over 3 factorial, and that multiplies x cubed. Let's keep going. Let's plug in C4. C4 was C0 over 4 factorial. And let's do 3 more. Let's plug in C5. That was C1 divided by 5 factorial. And then C6, we got that to be minus C0 over 6 factorial, x to the 6. I think the pattern's becoming pretty clear, so let's just do one more term. We're going to add C7, which is minus C1 over 7 factorial, x to the 7th, and then we'll do dot, dot, dot. Now we're going to combine our terms that have C0 in them, and then the terms that have C1 in them. This gives us y is equal to C0, and we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And that's going to continue. And then our C1, and those terms are going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and all the other terms. It makes sense that our solution has two constants in it, C0 and C1, because we're solving a second-order differential equation, and it will always have two arbitrary constants in the general solution. Let's now go one step further, and let's rewrite these series in summation notation. We're going to get y is equal to C0. Our first series can be written as the sum. N goes from 0 to infinity. The powers of x are even, and we have coefficients that alternate in sign. So we're going to write this as minus 1 to the n. That's for the alternating sign. And then we have x to the 2n, and we're going to divide all of this by 2n factorial. And then our second one is going to be C1 times the sum. N goes from 0 to infinity. Again, we're going to have alternating signs, so we have minus 1 to the n. Now we have odd powers of x, so we're going to write this as 2n plus 1, and we're going to divide this by 2n plus 1 factorial. These two series may look familiar to you. The first series is cosine x, and then the second series is sine x. So we can also write our solution as y is equal to C0 cosine x plus C1 times sine of x. The solution to our equation then can be written really in three different ways. We can write it with the series written out explicitly. We can write it in summation notation, or we can write it in terms of elementary functions if the power series is a known elementary function. And that's it. You now know how to solve a differential equation using a power series centered about x is equal to 0. You should now be able to work through some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.